Hello, this is Adam Ruck, and in this video presentation we will be discussing LiDAR and its relation to the definition of pointwise convergence. In this presentation of LiDAR and pointwise convergence, I will discuss a brief history of LiDAR and its recent developments through real analysis and various applications. In doing so, we will look at specific natural events that have occurred, like Hurricane Sandy in the fall of 2012, and other case studies which will help to highlight LiDAR's effectiveness and characterizing landscape change over time. In doing so, we will discover how LiDAR technology is directly related to the definition of pointwise convergence. We will then show the definition of pointwise convergence and prove the definition of pointwise convergence with an example. Hurricane Sandy was the deadliest hurricane of the 2012 Atlantic hurricane season, and as evident in Figure 1, the hurricane left damaged coastlines and infrastructure in its wake. LiDAR, however, can help us better understand environmental and ecological consequences following events of this magnitude to better prepare ourselves for similar events in the future. With that being said, let's discuss LiDAR. LiDAR is an acronym for Light Detection and Ranging, and fundamentally is an active remote sensing method for determining ranges by targeting an object with a laser and measuring the time for the reflected light to return to a receiver. Early uses of this technology were employed in the late 1950s, but the 1960s into the 1970s saw this technology being used to measure elevations of the ground surface, and subsequently produced the first topographic maps and DEMs, or digital elevation models. Recently, advancements in LiDAR technology have been used in unison with drone flights to map remote landscapes, areas on the ocean floor, and have applications in many disciplines, such as wind farm optimization. Figure 2 depicts how LiDAR instruments can be fitted to aircraft and satellites to carry out surveying and mapping. LiDAR sensors mounted on mobile platforms, such as airplanes or satellites, require instrumentation to determine the absolute position and orientation of the sensor. Coordinate data provided by satellite coverage then enhances the accuracy of LiDAR mapping through an aircraft's GPS receiver. An illustration of the process of a LiDAR system is seen in Figure 3, where light is emitted from a rapidly firing laser, similar to quickstrobing. This light travels to the ground and reflects off of things like buildings and tree branches, where the reflected light energy then returns to the LiDAR sensor, where it is recorded. A LiDAR system or receiver measures the time it takes for emitted light, or photons, to travel to the ground and back, and that time is then used to calculate a total distance traveled. This distance traveled is then converted to elevation. These measurements are made using the vital components of a LiDAR system, including a GPS that identifies the XYZ location of the light energy, as well as an internal measurement unit, or IMU, that provides the orientation of the plane in the sky. The distribution of light energy that returns to the sensor creates a waveform, similar to what can be seen in Figure 4. A waveform is a graphical representation of a signal in the form of a wave that gives us specific information about the object's characteristics. In these waveforms, the areas where more photons are being returned to the sensor create larger peak amplitudes in the distribution of energy, representing characteristic objects on the ground, like a branch, a group of leaves, permafrost, or a building. Figure 5 depicts the resultant collection of discrete points of LiDAR data after a survey, called a LiDAR point cloud. These point clouds represent spatial data as a collection of coordinates, and can handle large data sets for a wide array of processing. In this instance, with respect to LiDAR data, they are used as a middleman to turn the raw data collected by LiDAR processes into 3D models, such as DEMs or topographic maps, as discussed in previous slides. One of the most commonly used applications of LiDAR include using LiDAR to derive high-resolution elevation data, as well as extracting characteristics and information from certain landscapes, including species identification, tree canopy heights, and most importantly, how these and other landscape features change over time. Now we're going to pick apart Figure 13 from the Hurricane Sandy Observations and Analysis of Coastal Change Study conducted by the USGS. And we're going to use this study to evaluate landscape change as a result of Hurricane Sandy in Pea Island, found in North Carolina. Figure 7 is from the Hurricane Sandy Observations and Analysis of Coastal Change Study and looks at the shoreline change in Pea Island, North Carolina, prior to Hurricane Sandy and following Hurricane Sandy, effectively using LiDAR differencing to measure elevation change as a response to hurricane processes on the coast. Here we can see a three-dimensional digital elevation profile produced from the LiDAR point cloud data of a survey done in the area, and it becomes clear that the steepest elevations are adjacent to the roads along the beach, or the red colors seen along the figure, and relatively lower elevations, which are characterized by light and dark green colors on the figure. Similarly, Figure 8 here was produced using 3D digital elevation models, 3 years after the previous survey. There is a clear difference in elevation change across the beach roads, which were heavily eroded as a product of overwash in the area. What can we do with this knowledge that hurricane events and related processes can induce landscape change and severe differences in elevation? Figure 9, however, is a 3D elevation model that is slightly different than the two previously discussed, as this figure is a product of LiDAR differencing, which permits precise quantification and accurate mapping of a dynamic environment after an event of severe landscape change. By taking the pre-Sandy and post-Sandy models and effectively subtracting their topographic elevations, we can extract elevation changes as a product of Hurricane Sandy across the landscape. Here in Figure 9, it is clear that some of the most drastic elevation changes correspond to teal and red colors in terms of deposition and erosion, respectively. Prior to Sandy, the dunes in this area of Pea Island vary in height and width. During Hurricane Sandy, the lower and narrower dunes were overwashed by waves and storm surge that carried sand from the beach and dunes and deposited it on the roads and marshes in overwash fans. Significant new damage to the stretch of Highway 12 running through the Pea Island National Wild Refuge was caused by Sandy, and much of the roadway was buried under large overwash deposits as a result. As we can see from this study, we can use LiDAR technology and resultant point cloud data to model landscapes and better understand their evolution over time, as they're impacted by natural disasters, anthropogenic development, and other ecological factors. This is where the definition of pointwise convergence comes into play. Suppose we did a LiDAR scan of a plot of trees. Intuitively, we can think of the incline of the tree's sides and the rising canopy as slopes. Mapping these slopes as functions from a LiDAR scan, we can use resultant point cloud data to develop a sequence of functions that will eventually converge to accurate slopes of respective trees. We can then use GIS or Geographic Information System mapping software to capture and further analyze the spatial and geographic data. This procedure of research effectively demonstrates the definition of pointwise convergence. This brings us to the definition of pointwise convergence. Let f and x be defined by a domain A transformed to the codomain R, the real numbers, be a sequence. We then say that f and x, defined by our domain A, is transformed to the codomain fx, a function, if and only if, for all epsilon greater than 0, where epsilon is a real number, and we have a fixed known x in A, that there exists a natural number dependent on our choice of x and epsilon, so that the distance between f and x, our sequence, and fx, a function, is strictly less than epsilon, when n is greater or equal to n, where n and n denote specific sequences. This sequence fnx converges to the limit fx pointwise as a result. Here I will demonstrate an example of pointwise convergence, and in doing so, prove the definition of pointwise convergence. In our example, we consider the sequence of functions fnx equal to x squared plus nx, all divided by n, and I will prove the sequence converges to f of x, which is defined on set R, by using the definition of pointwise convergence. If we want to use the definition to prove pointwise convergence, we first need to do scratch work. We would like to show that the distance between the sequence and its limit must be strictly less than epsilon. This happens when we choose some n in the natural numbers bigger than some capital N. So our main goal is to find this capital N. First, we will start by computing the distance between fnx and fx. We make fnx and fx have the same denominator by multiplying fx equal to x by n over n, and then we cancel the terms nx and negative nx, and we are left with the absolute value of x squared over n. By using an absolute value property, we can then separate each absolute value. From there, we can then remove each absolute value for any real number squared is positive, and our denominator is strictly from the natural numbers, which are all positive numbers. Then, by the Archimedean property, we know that there exists an n in the natural numbers greater than x squared divided by epsilon. This gives us our choice of capital N. We can then choose capital N to equal the greatest integer function of x squared divided by epsilon plus 1 to ensure that the inequality holds, and that our choice of capital N works for all epsilon positive. Time to write the formal proof. For the formal proof of this example, we will first choose epsilon positive in R and fix x, which belongs to the set of real numbers R. We then choose capital N found in our scratch work, x squared divided by epsilon plus 1, when n is greater than or equal to capital N. We then have the distance between f and x minus fx eventually equal x squared over n. But n is greater than all capital N, and capital N is defined as the greatest integer of x squared divided by epsilon plus 1. So the distance between fnx and fx is less than epsilon when we take n is greater than or equal to capital N. This implies that this sequence fnx converges to the limit fx pointwise. Another useful application of LiDAR is producing maps of the subsurface, so researchers can effectively see features not visible to the naked eye. Here specifically, this particular hill slope contains gelifluction lobes, which are the more identifiable on Figure 10 by the intense waves of blue and purple stretching the hill slope. These gelifluction lobes were produced from the cyclic freezing and thawing of a once active layer. These nodular lobate structures are hidden by trees, vegetation, and rocks on the surface of the hill slope. Fortunately, by using LiDAR and stripping the surface of the hill slope, we can now see the subsurface and look at past climates of certain landscapes. Thank you for watching my video presentation regarding LiDAR and its relation to the definition of pointwise convergence.